Sorry, I'm so sorry. It was I was muted. Okay, just a minute. Okay, so let me begin with. So yesterday we talked about deep neural networks and convolutional neural networks, and you did lab when you did the classification problem. And then today we will talk about the state of the art CNN architectures, and I will also tell you about the encoder decoder models for image segmentation, so that in the next session, which is a lab session, Samir will help you to design models for segmentation. So before I begin with the architectures, I would like to repeat a couple of things regarding CNN. So just see, because I have a feeling that some of you were having problem in understanding this weight sharing and how CNN are basically helping us. So let us take this example again. So we are having this 6x6 image, and this is my 3x3 filter. And when I am placing this filter here on the picture, then what happens that these pixels are getting these weights. So you can see that the first pixel gets, you can match it with this color scheme, that the first pixel here that gets you muting me, Durgesh? Don't mute me, because so okay, so we are having this picture and this filter. So we are placing this filter on this picture, and then here these 9 pixels, these 9 weights, and by doing multiplication followed by addition, we are going to get this value corresponding to this position in the output image. Right now, here what we say that that how so here, what is happening when we are placing this filter? So we are connecting to 9 inputs only, not fully connected. Like if you remember fully connected layer, now every you can say neuron is going to get the weight here, right? But here what is happening? We are only connecting to 9 inputs at a time. So it is not a fully connected. And then, so because of this, we are getting fewer parameters, right? You need to learn these filter coefficients, right? That is what weight, right? You are learning here. Now what happens that when you are going to shifting your filter, now again what is happening, this filter coefficients are not being changed, right? So the same 9 coefficients, but the position in the image is changed. So earlier this 1 has got this 1, now this 0, here the second position will get this weight there, right? So that is what is represented here. And when you are going to place the corresponding weights here and doing the multiplication and addition, you are going to get this value that is corresponding to this pixel in the output image. So what happens when you are moving, the same filter is going to move across the entire picture, right? This is what is the example of the weight sharing, right? So in the weights are being shared among the input neurons, you can say. Here our input are pixel values. So because of this, these things, that a small filter first of all, and then so a small number of inputs are participating, and then we are doing sharing of weights. Therefore, we are having less parameters. Now we can compare this thing with the so that we may understand the difference between the convolutional layer and fully connected layer, right? Now let us say we are having our picture of size this 32 cross 32, okay, cross 3. Now when we, for fully connected layer, what we need to do, so first of all we will going to flat it first. So when we are going to flat it, we know that okay, when we are going to multiply this, we are going to get this 3072 elements. So they are being arranged in a column, right? So now what will happen, let us say our hidden unit, right, first hidden layer of this fully connected network is having 10 units, right? So what will be the parameters you need to learn? Now remember that each, and so 10 units are there. So how many weights, because every input here will participate, right? So every input is given a weight here. And so that all those weights are supposed to be learned. So how many weights for 1 unit of neuron? That is 3072 weights. And because we are having 10 units, so see 3072 multiply by 10, and then the bias is going to be added. So that is how we are having these trainable parameters. Now, if you compare this fully connected layer with the convolutional layer, let us say we are having a convolutional layer. So my filter size is 3 cross 3, and I need to extend it to the full volume of the image. So right now my image, let us say this here, 32 cross 32 cross 3. So I have extended my filter in the depth. So my filter is 3 cross 3 cross 3, right? Now with 3 cross 3 cross 3, just saw previous slide, 3 cross 3, 9. Now we are having 3 copies, right? So 3 cross 3 cross 3, that is your 27, right? 27, and then 1 is your bias. So this 27 plus 1, 28, and because here we are having 10 filters, so all 10 filters, all weights we are supposed to learn, so that is 280, right? So this is how we can understand this weight sharing. I hope the concept will be clear to you now. So now let us move forward, as you know that I told that since beginning, like since neural network came, we wish to apply them on the visual data. So if we talk about computer vision task, then we can see here object detection is one of the most interesting problem in the computer vision, right? Especially after it is being associated with the self-driving cars, right? Where the systems blend computer vision, LiDAR, and so many other technologies to generate the multidimensional representation of road with all its participants, right? So also we can say that object detection can be used in video surveillance, if you take another important example, or say crowd monitoring, just to prevent the terrorist attack, or it may be used for applications like finding interest of customers in the shopping center, like all sort of applications are there. So to understand the complexity, right, what is object detection and what is the complexity in this, let us start with the classification. Okay, so let us start with the classification first. So here in the classification task, we have an image, right? You can see this image over there, right? And we want to assign it to one of the many different categories. So maybe cat, dog, bird, car, whatever, right? So we want to assign this image a category, and that is our classification task, right? So basically here in the classification, what we are doing, we wish to answer the question, what is in the picture, right? So we are saying that, okay, this image is having only one category assigned to you. For example, here this cat category is assigned to this image. Now let us move to the next level, right? Next level, that is along with the classification, we have localization. So here we want to locate our object in the picture. Not only we are saying that this object is there, but we also want to locate where this object is there, right? So what is it and where it is, right? So this task is called object localization, right? So we can say, okay, so far so good. But in real life scenario, what happens? We are not interested in locating just one object as it is the scene here, but rather we wish to locate multiple objects in one picture, right? So again, if you talk about self-driving cars, then we need to find the location of other cars, traffic lights, different signages, humans in the real who are there on the road, right? And then we are supposed to take appropriate action. For example, let us say on the road there is a paper bag, or on the road there is a child, right? So your action will be different depending upon the situation, right? So this is the example of object detection. And in object detection, we are interested in finding out all objects in the image, and then we draw, as you can see, this is called bounding box, right? So we can draw the this bounding boxes, means that we want to find out the exact boundaries of our objects in okay, just to here we are putting up these boundary boxes here. Now next is that come here the next level, that when we say that there are certain situations where we want to find exact boundaries, right? Here you can see bounding box, right? But here we want to find out exact boundaries of our objects, and this is called instance segmentation, right? So we can say that CNN is a class of deep neural network which is most commonly applied to analyze visual imagery, right? So we'll do some tasks we have already done, and some tasks you will do in this course, right? So now let us again revise our this ImageNet large scale visual recognition challenge, which I introduced you yesterday, that since 2010, it is at 2017, it is offering challenges. And so the data set, that is ImageNet, that huge data set, and this brainchild of Professor Fefeli. And then how this CNN came into the picture. See here, this in 2012, we are having this first CNN based winner, that is your LXNet, right? So I will take you to a quick tour of this LXNet, so that you may appreciate what what lot has been done in this field, so that now things are much easier for you. So here, this what LXNet did. So this competition ImageNet classification. So he applied this deep convolution neural network, and when LXNet is processing here, this is your network, and when it is processing an image, this is what is happening at each layer. That is what I already told you in the CNN, that at each layer, the higher each layer in the hierarchy, we are learning higher order features, right? So from low level to high level features. So finally, at the final layer, we are saying, okay, the probability is assigned, okay, whether this picture is of cat or for a dog or whatever, right? Depending upon the like which category gets the highest probability, the image will be assigned to that class. Now let us see about this architecture, and try to understand what all these boxes means. So here we have 8 layers. So we are having 5 convolutional layers. So you can see first, second, third, fourth, fifth, right? So these are the 5 convolutional layers, followed by 3 fully connected layers, right? And we have here the ReLU activation function is used to add the non-linearity and improvement of convergence rate. And remember here, at that in 2012, we do not have that much infrastructure. So multiple GPUs were required for faster training of this deep neural network. And here you can see this parameter, these days you are having many models like more than these parameters. But at that time, having a model with 62.3 million learnable parameters, that was not easy task, not a joke, right? And so because of these high number of parameters, the model was very much susceptible to overfitting. And because of this, in this model, heavy data augmentation is done, right? So heavy data augmentation and dropouts is used to avoid the overfitting. And here the pooling is there, max pooling, as you can see. But yesterday I told you max pooling, that was of non-overlapping nature, right? We have used 2 x 2 filter, and stride was 2. So that we are placing it, then we are using actually non-overlapping pooling. But in this architecture, LXNet, they've used overlapping pooling. And see how what was the issue there at that time. We are having this model was trained on this GTX 580 GPU, which was having only 3 GB of memory, and therefore this entire network can't be fit onto it, right? Therefore the network was split. You can see this parallel, right? So the network was split across 2 GPUs, right? So you can say half of the neurons on each GPU, right? You can see this is split here in the architecture also, right? And see here, what is the thing that it took, like now you are doing in the lab, right? Very quickly you are training, you are doing testing and all those things. But at that time, because of course that data was huge, so and this model was requiring high computational resources. So it took 5 to 6 days to train on these 2 GPUs, this model, right? So I hope you understand how progress we have done so far. So just take this quickly here. When we talk about this LXNet, then input picture is your 227 cross 227 cross 3, and our first convolutional layer. See here the filter size. Till now, yesterday we are talking about small filters, right? Filter size. But here you can see a large filter, right? 11 cross 11 filter is used, and with the stride 4, and that is how we get this output layer of this 55 cross 55 cross 96. Now, how this 96 is coming? Because we are using 96 filters at this, right? And how this 55 cross 55, if you can get it, then this, remember this, I told you how to get this. If it is difficult to calculate Manually, you can use this formula. So just put the value of n, that is 227, value of f, that is filter size, that is 11, and just do this simple mathematics. So you'll get the 55 cross 55 cross 96 image, right? And so what are the number of parameters here are going to be used? See here, I gave you example. Now see another example. Now my filter is 11 cross 11, right? And my picture is 227 cross 227 cross 3. So I need to extend my filter to the depth 3, right? So these many parameters for one filter, right? And there are 96 filters. So for this layer, for this first layer, how many parameters are supposed to be learned? These many parameters, right? So I hope it is a very simple mathematics, and now it is clear to all of you. Still, if anyone is having doubt, please, you may ask. And the next layer, you can see that this is your max pooling layer, right? So here overlapping max pooling, as I told you. And then we have another convolution layer followed by max pooling layer, then another layers there. And finally, we are having this fully connected. Here you can see that fully connected and dropout layers. So in dropout layers, what we do is that we randomly set some input units to 0. Basically, they are not participating further with so we decide a frequency that at each step what will be our dropout rate. Then finally here we are having these 3 fully connected layer, and with here this finally output is 1000 neurons, and here we are using this activation function softmax, which assigns the probability of whatever input image is there and whatever classes you have trained. So let us say you have trained this for 4 classes. So it will softmax layer or function will assign the probability, will convert these it into the values into probability, and then you will get the whatever class. So you'll get 4 probabilities corresponding to each of the class, and the probability of a class is highest, the picture will be given that assigned to that class, right? So these are the different parameters and like that. So this is your AlexNet. Now these are the results. You can see here these classification results here, right? So see here, because how this is converting into, and the highest probability, that is how it is getting the this result. Now let us move further and see VGG, right? So VGG, that is the, you can say that although here you will say when we talk about 2014, actually for the classification task, the winner was GoogleNet, right? So, but as far as classification task is concerned, VGG was the first runner-up, right? But it has beaten the Google Net in the localization task, right? And still, this is one of the most popular image classification model, and many models later on developed on this basis. And so VGG stands for, basically, there is a visual geometry group in University of Oxford, and the researchers there, they gave this VGG in 2014, and this is nothing but a convolutional neural network model. So let us see some of the details of this VGG. So VGG architecture, it is very, you can refer to this paper. So very deep convolutional networks for large scale image recognition. Now here you can see that your picture 224 cross 224 cross 3, and these are the various layers, right? So here you can see that the first layer, you are using this 64 filters, right? Second layer, you can see you are using 128 filters. Third layer, 256 filters. Fourth layer, 512 filters. So you can see that as you are moving forward, you are increasing the number of filters, right? But what is the what is this architecture stands for? See, you can see that here this contains 13 convolutional layers, right? And 3 fully connected layer at the end. You can see here, right? 3 fully connected layer here. Now here you can, here the important point is that earlier we just saw in the AlexNet, they use 11 cross 11, right? So some other models, they also use a large size filter. But here there a trick was being played, and why I am saying that it is a trick, I will tell you. So here we have used smaller size filters, right? Not the big size filter. So 3 cross 3 for filtering, for convolutional layer, 2 cross 2 max pooling. And then but still because of you can see so many layers, and the model was very slow to train, right? And when the model is stored on the disk, then it is occupying a large scale now, large space. Why? Because the total number of, you can calculate it also. Now I told you how what is the method to calculate that total number of parameters here you are 138 million, right? So 138 million parameters, when they are stored, 500 MB space they were taking, right? So here and not this is, so when we say VGG, basically this is a VGG 16 architecture. Okay, I will upload it in slide. So VGG 16 architecture, and later we have a deeper variant of VGG, that is VGG 19 also. Now this is the like, if you are not able to understand that big picture, now it is easy to observe in this picture. So input is there, then you can see these convolutional layer followed by the pooling. So here we have used basically we have reduced the size of the convolutional kernel and we have increased the number of convolutional layers. Right here you can see that earlier I showed you one convolution layer followed by, let us say, max pooling. Now here so we have increased these layers, right, and size of the convolution kernel is decreased. Now what is the how this is possible? Basically, how can we replace like a larger filter into a smaller filter? So basically we are actually decomposing a larger filter into a smaller filter. How? You can see that if we are having, instead of using this 5x5 filter, we can use 2 3x3 filter. So what we'll do, instead of using one layer of 5x5 filters, we'll use 2 layers of 3x3 filter, right? And effectively it is giving you the same receptive area. How? You can see that, okay, in the first layer, like let us say this, okay, so because 3x3, let us say this filter here, 3x3, this filter here. So effectively what is happening? We are covering this entire 5x5 space. So our receptive field is not changing, right? Similarly, let us say we are having a filter of size 7x7. So we can, instead of having one layer of 7x7, we can have 3 layers of 3x3 filters. Now you must be wondering that what are we doing, right? Because ultimately when we have reduced the size of the filter, we have increased the number of layers. So how does it helping us? Basically, remember why there is another reason of doing this, because this gives me lesser number of parameters to learn. Just see this example. So in the AlexNet, what happens that we are having this one layer of 11x11 filter, right? So how many parameters? 11x11 cross 3, right? So okay, so okay, one layer. So okay, 11x11. Now let us say we are having 5 layers of 3x3 filters, right? So 3 cross, and definitely we will take in depth also, so that will be here also and there also. So 5 layers of 3x3 filter, and what will be the number of, so 3x3 filter, 5 layers, 45. So you can see that parameters are reduced, right, a lot. So that is the simple trick we do. Like if you go the image processing, then what happens that we would like to decompose. We want decompose our filters into 1D filter. So in place of 2D filter, we are applying the same operation with 1D filters, and we are saving the computations. That is a very known technique. So that is why we wanted our filters to be separable. We call it separable filters, right? Now here we are talking about larger network, because the networks are larger. They are more hungry for the training images, and so they are going to, let me complete it. I will give. So when we are going to increase this here, see here what is there. We are saying that because you are covering the same thing, right? Your receptive field is not changing, so it will not affect, right? When the receptive field will change, means whatever information we are getting through one filter, we are not getting it through that filter, then it is a problem. Here we have reduced the size of the filter, but at the same time we have increased the number of layer, right? So that is how I showed you here that the receptive field remains same, right? So so here the fewer parameters, they are better for the faster conversions, and they reduce the overfitting. So these are the various VGG configuration you can see here. So this is VGG 11, VGG 13, then VGG 16, and VGG 19. So here you can see that this introduction of these layers here, right? So maybe this VGG 16 here is giving you good performance, right? So here you can see that these are the performance denoted on a single scale evaluation. Now, what do you mean by single scale evaluation? That all images, right? Because are here you can see that we are using of same size. Now, after VGG, let us take another very important network, deep neural network, and here the technique which helps us a lot in the upcoming deep neural networks. So ResNet 152 was the winner of 2015 contest, and so context was basically for classification as well as localization and detection. So those who want to see what was there, if you just search it with this, then you will get the result of all the models, right, whomsoever participated in that competition, and then the top one. So you will get what are the, let us say, what is the results for classification, what are the results for localization, and that is how I told you that this VGG 16 beat Google Net in the localization task, not in the classification. And this ResNet so architecture came, which was the first, you can say, really deep network that more than 150 layers. And this was also winner of MS COCO 2015 detection and as well as segmentation. And if you see those who are working in the area, they know that CVPR, that is a top-notch conference in the field of computer vision. And this paper was published in 2016 with more than 19,000 citations. So very interesting. So this is a very deep network of up to 152 layers by learning here the important thing is what, that it is learning the residual representation functions instead of learning the signal representation directly. So I have given you a hint about the skip connections yesterday, and I told you that because we were fighting with the vanishing gradient problem. So what was the solution there? First sort of solution is being thought of. Okay, let us change the activation function. So that is how from sigmoid we came to ReLU. And then another very nice solution was provided in this ResNet architecture, that is your skip connection. Now, skip connection. So what we do is that basically a skip or a shortcut connection is added here. So you can see that because now we know that my output may become, because of the vanishing gradient, my gradient values become so low, it goes close to zero, and effectively my network is not learning. So what we are doing is that we are providing a skip connection, right? We are providing it the values, right? Here they are simply going to be added here, so that we are actually ensuring that the higher layers should perform at least as good as the lower layer, right? And not the word. So we are not allowing gradient to vanish. So here what happens that usually, so let us say we are getting some depth here. So okay, so let us say 32 or 16, whatever is your depth. So you are getting those many layers, right? Those many outputs. And here what is happening, whatever is the output of your previous layer, just apply pointwise convolution, let us say. So you'll get one activation map and then add the values into the output maps here, right? So that you are not allowing them to die, right? So the output becomes what? Here the output becomes your this. This fx is the output here, and the x is that shortcut which you are adding. So what we say that actually when we are saying that we are learning fx, that is we are saying, okay, this is kind of a residual, because when you are learning it, then you are adding x. So you are saying, okay, we are actually learning this residual, right? So even if there is a vanishing gradient for the weight layers, we will always have this x, right, to transfer back to the earlier layers, right? So that the performance will not be degrading, right? It will be, at least let us say your fx becomes 0, right? So you are having this x there. So the performance is at least that. So, I mean, I'm sorry I mean, this slide, it is difficult to visualize. You can have it on your system and see here these three deep neural network, VGG19, this 34 layer plane network, and this 34 layers residual network, they are being shown here. And here you can see that if you go through this, you will understand what is the meaning of it. So here you can see every detail is there. So image, then first of all, 7x7 convolution, 64 filter filters, right? And then pooling is being done with 2x2, then 3x, then again convolution. This time now you can see that 3x3 convolutions are there, and these 64, these are the number of filters, and here you can see the skip connections, right? So that is how your ResNet 152 model is there. So I'm introducing you, you can see it today on your system, and better have a look at it. So when we say that, okay, this ResNet 152 architecture, it uses most, if you look at here, most of the filters are 3x3, except here this 7x7, right? And here we do downsampling, that is with stride 2. And then global average here, instead of max pooling, we use global average pooling, right? Okay, sorry, this yeah, this pooling is done here, and but at the end here we are having this. So this is your average pooling layer. I'm sorry, I told you there. So this is your average pooling, global average pooling layer, and the 1000-way, right, a fully connected layer you are having with softmax at the end. So again, your softmax will convert these values into probabilities, 1000. So you will say, what is this image about? So here, because our network is going on deep, so definitely the time complexity is high, and therefore a bottleneck design is also being given, so that the complexity may be reduced. So here you can see that this is your basic block, right? And this is your bottleneck block, right? So bottleneck design, basically here you can see that this 3x3, 64 ReLU. So here what is happening, we are going to add this 1x1 convolutional layers, and which are added to the start and the end of the network, right? And because of this, what happens that, remember this point-wise convolution, 1x1 can reduce your number of connections, definitely parameters, but it is not degrading the performance of the network so much, right? And what is the, with the bottleneck design, your 34-layer ResNet becomes 50-layer ResNet. So basically you are adding this, so not much complexity you are adding. And why it is called bottleneck design, you can see here 64, 64, 256, right? So it is increasing like. So in comparison to basic block, this is your residual block, right? See, optimizers are going to be used while network training. So in every network, you are going to use that, right? It is not like in any specific. So so this is your ResNet architecture, and here we are having so with the bottleneck design, we are having deeper network. For example, okay, this ResNet 152, ResNet 101, like that. So here, this is the ResNet overall architecture. So here you can see, okay, what are, this is 18 layer, 34 layer, 50 layer, 101 layer, and 152 layer. So here you can see that all details are given, 7x7 filters and 64 filters here, max pooling with the stride 2. And here you can see the filtering is done. So stride is 2, not 1. Okay. So this is how, and you can see that here are the flops. Right. So ResNet 152, what are the flops? These many flops are there, right? So if you remember, we just talked about the VGG, right? So VGG 16 and 19. So remember I told you 15.3 to 19.6 million flops, right? And if you just see this ResNet, so even still it is flops means how many operations, floating point operations you need to do for this model, right? For classification, training and classification. So floating point operations, right? So these many flops. So if you go for the flops, then from 15.3 billion in flop in VGG to this, you can see it is still having much deeper than VGG, but still having lower complexity than VGG, right? So this was the beauty of this architecture. Now let us come to the deep learning models on mobile. Right. So mobile means that for mobile, like let us say you are moving, self-driving cars are there, drones are there, as you can see here, robots are there. So of course your mobile phones are there, right? So Google glasses, all those things. So what is the, when we talk about deep learning on mobile, then basically, if you can see all these applications here, they are battery constrained applications, right? So the mobile applications, they are having special requirements. For example, they are having low battery. Therefore, we need we can't have those large size models, right? And so we want small size models, cost effective, right? But their inference time should be short, right? Of course, cost should be less. And at the same time, we want so we are saying, okay, small size. So we want a small here memory. So not low battery is related with. So battery, then your memory, less number of parameters. We want that our model should be less data hungry, right? And at the same time, we want it should give us quick response, right? Your inference time should be short. So what does it mean that basically for mobile applications, we want a small model. Now, a small model means basically we need to uh, compromise, right? There is a trade-off. So there is at and one end it is accuracy. So definitely when you are reducing your model is uh, small, right? A lightweight model. So accuracy, I mean, you are going to, there will be slight drop. So, but at the same time, because we need this energy and model size, that is at most important for us. So we have to compromise it. So we need to get a model where we want to get like high accuracy at the same time, less energy, less cost, less small model size, right? So if we see the computational neural network, then let us see from where this computational cost is coming, right? So this is a general network here. You can see that certain convolutional layers are there, then fully connected layers are there. So how this cost is coming? Basically, how many filters you are using, right? So at different layers, you are using different number of filters. So first factor is how many filters you are using. Second number is that definitely, right, depending upon when you are using large number of filters. So for the next layer, there will be large channel numbers. So channel numbers for image input, or you can say feature maps. And finally, what is the size of the feature map, right? So when we go for small deep neural networks, so there are several things we need to, I mean, we can do so that we can make our model light. First of all, we need to remove the fully connected layer. We can't have so many of these fully connected layers. And another size is that we should go for filter reduction. Filter reduction means that from, let us say, we just saw that 3 cross 3, right? That now from 3 cross 3, let us say, why not we go to 1 cross 1, right? Small size filter. Then channel reduction, and at the same time, depth-wise separable convolution. So this first technique, kernel reduction, that is being followed in, there are so many, if now you are, those who are already working in the field, they are aware of it, but those who are new into it, they will see that, I mean, every other day we are getting new networks, right? So this kernel reduction technique is followed in the SKUSNet. Then this depth-wise separable convolution, that is followed in the mobile net, which is a very, I mean, famous model. Then if we talk about both this channel reduction as well as depth-wise separable convolution, then we are having this shuffle net. So these are all models, the small deep neural network, lightweight models. I mean, definitely we don't have that much time so that we can discuss all these models there, but let me talk about this mobile net. Or maybe let us see what do we mean by this reduction. Okay, first of all, see how we can do kernel reduction. Basically, we want to reduce the size of the filter, height and width of the filter, right? Now, what happens with the point-wise convolution, this 1 cross 1 filter? Because when you will place what happens when you place a filter on a image? So what happens, let us say you are taking a 3 cross 3 filter. Now you are placing it on the image on this pixel, right? So all these pixels are also participating here in this. So what is happening, you can see this, your filter, through this filter you are considering the effect of these neighbors on this pixel. But when you are having this 1 cross 1 point-wise convolution, so you're going to place it here, and definitely you can't see outside this 1 pixel radius, right? But still, what happens, these 1 cross 1 filter, they have the ability to combine and reorganize information across the channels. Across the channel, information is there, so that can be combined using these point convolutions, right? How, we will see. Now, somebody was asking this question also, what happens when we reduce the size of the filter? Here, this example is also there. So when we have here in the SKUSNet 2016, which came, like I told you in the previous slide, so it was observed that we can replace half of the 3 cross 3 filters with 1 cross 1 filters without diminishing without, loss in accuracy. Similarly, in the SQSnet, another version which came in 2018, here in this model, they actually eliminate most of the 3x3 filters, and by this, we call it filter factorization, right, which is there in the this inception net also. So 3x3 filters to 1x1, 3x1, and 1x3 filter, and still they manage to retain the accuracy, right? So with the small filters, our work is reduced, right? That way, parameter learning and all. So here you can see that how can we decompose larger filters into a smaller one. So this thing I just told you, what we did a trick in the VGG16, that we have constructed 5x5 support from 3x3 filter. So we have used two layers of 3x3 filter instead of one layer of 5x5 filter. And effectively, we are going to cover this entire area, right? Receptive area. And another example which I was giving you, that separable filters, right? So here what is happening, instead of this 5x5 2D filter, we got two 1D filters, right? This is, you can see, column filter, row filter. So what happens that instead of applying, this is a very famous technique, right? We use it in the image processing computer vision, that we want whenever we do filtering, we want separable filters, right? Because 2D operations, they take more time, 2D filter, right? Instead of having two 1D operations, there is a saving. I will show you also. So here, this in this Google Net Inception v3, v4, right? What we are doing, we are just decomposing this 5x5 filter into two 5x1 and 1x5 filters, right? So these filters are applied sequentially, and that is how what is happening. See, when this just a minute. See, this is going to be moved here, so all columns will be covered, and similarly, when this row 1 will be moved, all rows are being covered, right? So it is basically completing the yes. See, that is what I am telling you, that by reducing the size of the kernel, right? What trick we are applying, that we will reduce the number of operations, right? Number of our execution time. But I showed you the example that when people have observed, we are not getting that, sacrificing on the accuracy. So that is how these famous, like Inception Net is another famous network where we call it filter factorization. Okay. And we are saving a lot not at the cost of accuracy here. So now that was the kernel reduction, and now it is channel reduction, right? So reducing the number of channels. So if we just halve the number of filters in a layer, right? So what will happen? For the next, so for example, your first hidden layer is having 64 filters, right? So now the second hidden layer will get input as a, or you can say output of the first layer will be what? Will be having depth 64, because we have used 64 filters in this hidden layer. So if we just, let us say, instead of 64, if I'm using 32 filters, then what will happen? Our output volume from this layer will be having depth of 32, right? So this is one way of, so this is how we are reducing the we can reduce the number of channels. Now, another very important concept here is there, that is of depth-wise separable convolution. So depth-wise separable convolution, it is also called group convolution. So if you remember the standard convolution operation here, see here, this is your image, your 3 input channels are there, and then let us say we are having 2 filters here, so corresponding to each filter, right? So we need to see depth is 3, so filter is extended here, and we are getting one output channel corresponding to this filter, and the output channel corresponding to this filter, right? So what we did here, remember that when we placed this, then see here, so this first filter on the, let us say, red channel, green channel, blue channel. So then we did these 9 multiplication and these additions, this same process for the other 2 layers, and then we added it all, and then we get the pixel values in the output layer corresponding to this pixel, right? So this is your standard convolution operation. Now see what is, instead of this standard operation, what we'll do, we will do depth-wise convolution followed by point-wise convolution. So what we'll do, we are going to, we are not going to, we are simply calculating, right? Applying filter here on the separate layers, right? And then we are going to make use of this 1D convolution to get the same. So output is same. There is no difference in the output. If you look at the convolution and this standard layer, again, I mean, the same output you will get here, but here all the steps you are doing together, right? But here what is happening? Divide and conquer. So what we did is that we perform, first of all, these separate convolution, right? These separate depth-wise convolution, and then we use this point-wise convolution for adding, and this saves us a lot, right? Now, I will show you, if we compare this standard convolution and the depth-wise separable convolution, then, okay, so let us say this is my filter. So filter size is dk. So dk cross dk, and there are these m, this, yeah. So m is your number of input channels. So what happens in the convolution, this is standard convolution, we are going to have this entire thing in one go. But in the depth wise, what we say that we break it, right? So we do it for each channel separately, and then we apply this 1x1 convolution, point-wise convolution, to get one output here. Now see how it affects. So let us say when we talk about the standard convolution, what is the computational cost? See here, now let us say dk is the depth of the filter and df is the depth of the feature map, right? And m is the number of input channel, n is the number of output channel. Now what happens here? So first of all, you are going to how many because let us say you are having your 3x3. So how many multiplications are 3x3 filter? How many multiplications are there? 3x3. So these many multiplication there. Now there are m channels. So in each channel, you are going to perform these many multiplication. So let us say we are having 3x3. So 9 multiplication, 1 for red, 9 for green, 9 for blue. So total 3x3 cross 3. So here dk cross m, right? Then see how many filters are there. So let us say this this is the feature map, right? What is the size of your feature map? And on this feature map, you are going to apply this filter, right? And how many number of filters are there? Let us say you are having n filters. So for each filter, you are going to perform this task, right? So this is your complexity there. Now, if you break this process into two process, then what is happening in the depth-wise convolution? So what is happening here? First of all, you did this, right? Now here, what is happening? This you are not combining the output of different channels. You are doing operations on different channels separately, and then you are using this 1D convolution for combining the output from all channels there. So cost of this depth applying, and then cost of this point wise. And if you just see what is the reduction in the cost, so this is how you will get just the reduction in the cost. And if we are going to use, remember, see here, these numbers there, they are very important. So if you are making use of 3x3 depth wise separable convolution, we get improvement, right? Or you can say reduction in the computation 8 to 9 times, which is a huge reduction over there, right? So instead of, these techniques are being followed just to make our task easy, right? So what happens with this? Let us move to the mobile network, and here mobile net v1, right? So here you can see that mobile net. So your mobiles can be, you can use this classification task, detection task, right? Face detection, right? Recognition, that is there in all cameras over there, right? So you can do all these tasks on this mobile. So this is the model. Now what is there in the mobile net? As I told you earlier also, that at the core of mobile net, what is there? We are using depth wise separable convolution. So so what is happening? It is based, basically mobile net v1 model is based on depth wise separable convolution. So they are nothing but a form of factorized convolution, right? Which I just explained you. So this is your more details. You can see the basic point I have already told you. So here you can see this depth wise separable convolution is being used. Now here, this is just one example of object detection using mobile net. So this is a single shot detector object detection model. So in this course, now you are learning things in the stepwise manner. So you have learned classification. Today you will learn segmentation, and in a in the next week you will be learning object detection also, right? So this is this single shot detector SST object detection model. It is using mobile net as the backbone, and that is how it actually achieves this fast object detection, which is optimized for the mobile devices, right? So these are the results shown. Now, let me first discuss the thing which for which you are going to supposed to do the lab, and then I will come back bits on the autoencoder, right? So let me first of all, okay. So now come to the image segmentation. So the classification thing we did, and now this is segmentation. So I just gave you the example of instance segmentation earlier in the beginning of this lecture. So here you can see that there, when we talk about instance segmentation, where you want to get the exact boundaries there. Here, the semantic segmentation, you want to highlight that area basically, and in the instance, you want that exact boundaries over there separate. So output of the semantic segmentation, remember that segmentation is one of the most difficult tasks in the image processing, right? So output of the semantic segmentation here is not just a class label, right? So here we don't want, I mean, it is not only just to get this class label, but we also want these you can say this full image, right? So this a complete high resolution image in which all pixels are classified. So here you can see that the pixels which are black, they are classified as background. The pixels which are in pink, they are classified as a person, right? So, but if we remember your typical convolutional network, if you remember, I told you there when we talked about, I especially mentioned when we were talking about VGG, that what we did, we reduced the size of the filter and we increased the number of filters, right? So that was there. So instead of having one 5x5 filter, we are having 2 layers of 3x3 filters. So layers are increased. Now, what happens in a typical convolutional network, that height and width of the image, naturally, they are going to reduce because we are doing pooling. So, the filter in the deeper layer, why we are reducing this? So what is happening here? So, so because of this size is decreasing, therefore, the filters in the deeper layers, they may focus on the larger receptive fields, right? Concept. And but when we are increasing the number of channels, right, or the number of filters, then they are actually helping us to extract more complex features from the image, right? So what happened in this process? In this process, actually, when we go for the typical convolutional neural network, it actually tells us what is there, right? But actually, we lose this information. Where is this information, right? So classification focus is on what is there, right? But where it is there, that information we actually lost in the regular convolutional network. So, but in case of segmentation, when we talk about, then we need both sort of information. We need what is there, and at the same time, we need where this information is there, right? This means that as an output of this CNN, we need to upsample the image, because my image is going to be smaller and smaller in size. So, but we can't, at the end, we can't afford, we want to equal that same size image over there, right? Where we are having these areas marked, right? So this is this area, this color area belong to person, this color area belongs to background. We may have more objects there, right? So let us say some trees there. So that is with some other color. Let us say this is of tree, for example. So it means that we need to upsample the image. And what does it mean? We need to convert, when we are reducing size, means we are moving towards low resolution image. So from the low resolution image, we are again supposed to go back to high resolution image so that we can recover the where information, right? Where is this? So when we go for deep learning based segmentation method, it is a typical encoder decoder architecture. And here this is a supervised, they come under the supervised learning techniques, where with the training data, we also provide corresponding ground truth. So here you can see that this is a simple encoder decoder model. So maybe Samir will take you because this belongs to his work only, wireless capsule endoscopy, and where the polyps are there. So this segmentation, it is taken from one of his work only. So here you can see that encoder decoder model is there now. So what is the task of the encoder basically, right? Encoder extracts the important feature of the objects, right, in which you are interested, and what is this output of the encoder is a feature map, right? And feature map are basically smaller in the scale, and but they have only relevant information here, right? Now see, the size is reduced because in encoder downsampling you are doing, so size is reduced. Now again we need to do upsampling because the output we want the same size image there. So decoder tries to upsample the image, right? Basically against convolution we need to apply deconvolution, you can say, and upsample the image so that you can locate the regions which are belonging to the object of interest here. So let us say this area, this is, he's calling as polyp, right? So this is what is there. Now here you can see that, so now input will be not only the image but also the mask. For example, this is a 2-class image, right? So we want to segment our picture into 2 areas, right? So let us say one area belongs to your disease class and one non-disease class, right? So here or background you can say, right? So here you have created 2 masks, right? In one mask, the area in which you are interested, that is white. In the other mask, the other area, so the you can say the negative of the other mask, right? So along with the this input image, you need these ground truths also, because these ground truths will be used at the decoder end. So we'll discuss how. Now, also before, we move for segmentation. So what are the performance measures we use for segmentation? One is intersection over union. So here you can see that when, let us say, your bounding box is this, right? Your actual is this, but you are getting is this, right? So that is a poor localization, right? Poor segmentation. So here you can say that area of overlap and the divided by area of union. So basically what we want uh, to improve, right? We want to improve the overlapping of these 2 boxes, right? Similarly, there is another parameter here, that is your dice score, and what this dice score says that, okay, twice of the area of overlap divided by sum of the areas of both images. So if you look at both the measures, basically they are trying to whether in any measure you take, we want a higher score, because a higher score will indicate a better performance. So it will lie between 0 to 1, right? And here you can see the example. So this is your intersection over union 0.4, 0.7, 0.9, right? See the actual ground truth and the one which is given by your network, that is quite exact, right? So it is 0.9. So higher values means that better performance. Okay. Now when because you are you are going to use this small model there for this, so let us discuss a very state of the art model, that is unit. Although it came in 2015, but this is this was revolutionary in performance improvement, and still, right, this is the first model we think of when we go for segmentation, right? So this model was basically developed for biomedical images, and it gives us the answer of the 2 questions which was there. We not only want what is there, we also want where is it, right? So unit is, again, as I showed you in the previous slide, it is an encoder decoder convolutional neural network, which is having massive, extensive use in, of course, for medical imaging it was given, and we are using it, like Samir is using, another student Amit is using, and so many students are using. And not only in the medical imaging, then autonomous driving, satellite imaging applications. So this unit is being used, right? So why I have chosen this unit here today, and we will discuss it in detail, because more like all those novel architectures, right, they are actually which are coming, they are actually somewhere having this unit as an intuition. For example, 2 unit are connected there in a paper we are just going through, that becomes your WNet, right? So maybe, as I told you, Samir will take you to the wireless capsule endoscopy, polyp segmentation. So here, what is the output of unit image segmentation? That will be a mask, right? Which will tell you the pixels belonging to which class, basically. Okay. So why it is called unit? And actually, it is getting its name from its architecture. You can see this U-shape architecture there, right? So and here, this U-shape architecture, it is comprising of convolutional layers mainly. You can see here, convolutional layer. And then we are having two networks here, right? Encoder, decoder. So encoder is there for, here you can see that downsampling, and decoder is used for upsampling, right? And here we are making use of skip connections, which I introduced you, given by ResNet, and here we will use it very effectively. So this architecture, we can say that encoder means contract, because it is reducing size, downsampling, contracting path, and decoder is expanding path because it is doing upsampling, right? So encoder path actually helps you to get the context information of the images, and decoder path gives the does the localization. Let us see how. Here you can see these, okay, this is your contracting path, this is your expanding path. And here just understand the meaning of these symbols. These blue arrows, they are denoting the convolutional layer, 3x3 convolution filters. So 3x3 convolutional layer with the ReLU activation function, right? These gray lines, they are actually a skip connection, right? So what we'll talk about later. So what, as I told you, that skip connection. So basically at the output of the decoder, we will provide this output from the encoder, so that we are helping decoder, right, for doing the, when it will do the backward flow of gradients, right? So these blue are your convolutional layer, gray is your the skip connection. Now this is your pooling layer, right? So max pool 2x2, right? And now, so this is your convolution and max pool. Now here you can see these green ones are up convolution, right? So you are here, you are decreasing size, here you will increase size, right? And finally here you are having this pointwise convolution, sorry, this one, right? And here at the output you will get the segmentation map. So let us see one by one. So this is a very typical architecture of a convolutional network, because here you can see this architecture of encoder. The convolutional layers and pooling layers are there, right? So what is there in the conventional convolutional network? So now let us first talk about encoder. So encoder, we are having two. Here you can see that 3x3. Here you see this 3x3 convolution. Remember here it is unpadded. That is why you can see that 572x572, and we are getting 570x570. Why? Because this we are not using the padded version, right? And each one is followed by ReLU, right? So ReLU activation function. And for pooling, we have used 2x2 max pooling with stride 2, right? And at each downsampling step, we double the number of feature channels. See here, remember what we are doing? Because our image is becoming smaller and smaller. So what is there? We want to learn more and more features over there. So we are increasing the number of filters, right? So here you can see that in the first layer, we are using 64 filters, then 128, then 256, then 512, like that, okay? Now, if we talk about decoder part, then here you can see that this upsampling is supposed to be done. So the feature maps, see here, when you are having here, now what is happening? This up convolution. So here this 2x2 up convolution, I will discuss later. Right, and then we will apply, see here, this skip connection. Skip connection is what? See this, what is happening here? See this 512, right? So 512 is coming from here and 512 is coming from here, right? See this. So this becomes 1024. So you are what these output maps, remember here 512 layers are there. So these 512 layers will join here, so that total there will become 1024 layers. So you can see that at each step, here at the decoder end, there are two parts, white part and blue part, right? So blue is coming from here, right? And white, that is coming from here. So one, basically we say that we are just stacking them, right? So first of all, whatever layers are there in the decoder, and then what layers are there from the corresponding encoder layer. So those are being stacked. Now here you need to remember just one thing, that because here we are following this unpadded, right? So we are not using padding while convolution. Therefore, size of the images are decreasing, right? So here you can see that we are having image of size 64 cross 64, right? So we are having here 512 filters, right? 512 filter output, 512 depth with size 64 cross 64. Now these 512 will be put next to the 512 here, but the size here is 56 cross 56, but here the size is 64 cross 64. So we need to crop these outputs, right? We need to crop these activation filter maps, and then we are going to put it. But if we are using padding, then there is no problem. Whatever size is here, the same size we'll get here, right? Now let us talk about skip connection. So here we need to perform, see, corresponding to convolution, we need to perform deconvolution, right? So basically upsampling. Now there are many methods of upsampling here, nearest neighbor, then this bilinear, bicubic, or sort of samplings are, upsampling methods are there. But here which method we use that is more popular in the deep neural networks, that is transposed convolution, right? And so here for two things are being done. For upsampling, we are going to use transposed convolution. I will discuss it. And then another thing we did, this skip connection, right? So the stack of these maps are there. Now, what we do, we actually, so as I told you, we concatenate the transposed, this convolution layers, which we got from here, and the feature maps, which we got from the encoder, right? So we are putting it here. So the two consecutive regular convolution and the model, why we are doing this, remember, to tackle this gradient vanishing problem, and also so that our model will, and with this our model will also, this will help our model to learn more precise output. Now, and finally what is happening here, so here this final layer, this 1 cross 1, this point-wise convolution is used, so that each of these 64 component feature vector, we get the desired number of classes, right? So here you can see that 2, right? So remember, if it is a binary segmentation, right? Which example I gave you, that in the image we are having two sort of areas, okay? So we want two basically maps for two classes, right? To segment 2. So that is why here the number is 2. Now, if and if you look at this total, then in total there are 23 convolutional layers, right, which are used in this unit model. Now here we can say that at last we need feature vector, right, to that which is equal to the desired number of classes, right? So why we are getting 2 here, as I told you, that because let us say we are talking about here, this is a standard architecture they gave, and here they used it for binary class segmentation, okay? So now we can train a network by calculate. So see now, till now you are making use of input image. I told you that along, because this is a supervised, it comes under supervised learning category. So along with the images, we need the mask also, right? Ground truth also. So now here you are having those two ground truths, right? Ground truth for class 1, ground truth for class 2. And so corresponding map, right? What will happen? The error is going to be calculated like as you do in the training of convolutional neural network. So the loss will be calculated, and then the back propagation will be done. And that is how your network is going to be trained. So that we are saying, okay, your model is giving you the perfect segmentation over there, right? So let us say this is the use of mask here. So the image is being provided, and here you will get two maps, right? So let us say one map is this, another map is this. So here you just calculate the error, right? So this is the map when you are considering this as this is for foreground, this is for background, and then you are calculating the error function and doing the back propagation using the gradient descent method as we do. Now, it is not like we can go for higher categories also. For example, if you look at this here, so here this is inside the cat, right? This is your outer area. This is your, let us say, background. So here we are saying, okay, 3. Similarly, let us say in a picture, okay, this road is there, this house is there, this tree is there, right? So I mean, different classes, different colors you can. That is how when you are having more than 2 classes, then different colors will be used. So definitely, if 3 classes are there, here we are going to get the 3 feature maps at the end, right? And then we are doing this calculation and all. So now come to, this is very important operation for us to understand that what are we going to do in the deconvolution, right? And at the time of upsampling. Remember that, I mean, mathematically we say that, okay, deconvolution, what is deconvolution? Just inverse of the convolution operation. So when the convolution on X gives you Z, then the deconvolution on Z should give you X, right? But what we do here we use actually we use the transposed convolution to reconstruct the image of the same size as the input image, right, on which the convolution is being applied. Now see, this is very important concept of this transposed convolution. Let us say this is your picture and this is your filter, 3x3 filter, right? Now when we will apply convolution, what will happen? We will get output. How? So what happens when we will apply it? Then we will get this output. How do we get this output? See from 4x4 picture, we are getting this when we applied 3x3 filter, we are getting our output 2x2. I hope this is clear to you, because what is happening when you are placing your filter here, right, and here, so one placing, second placing, then this third placing, and this fourth placing, right? Then only your filter is entirely within the picture, and that is how you are getting 4. So when these 4 pixels are serving as a center pixel, right, you are getting these 4 values. You can see also here that this 4 multiplied by 1, 3 multiplied by 0, 2 multiplied by -1. So what is there? 4 minus 2. Then this 1 multiplied by 2, that is your 2. Then 4 multiplied by 0, 3 multiplied by -2, that is -6. Then 2 multiplied by 1, that is again your 2. 1 multiplied by 0, and then this 3 multiplied by -1, -3. Right. So 4 plus 4, 8, and then -6, -8, -11. So -11 and 8. So what is happening? That is how you will get the results here. Now, so what happened after convolution? An input which was having 16 features is converted into 4x4 picture, converted to 2x2, right? So 16 features converted into 4 features, right? Now, what we will do in the transpose convolution, that so see how this is happening. So when we are applying filter on the image block, when I'm placing this filter over here, then at this time only these 9 pixels are participating, right? These pixels are not participating, right? So the contribution of these image pixels is 0, okay? And when I'm putting this mask here, I'm getting the first output over here, okay? Now let us, if we think that our filter size is same as that of your input image, right? So we are saying, okay, let us say my filter is also 4x4 because my picture is 4x4 here, and I'm saying that remaining entries are all 0 here, okay? So we are having non-zero entries at the 9 position only, and then we apply this convolution. So see what is happening. We have arranged our these image, right? We have in this 1D array, right, for convolution, and here you can see that our filters. So you can see here 1 0 minus 1. So 1 0 minus 1, and the next is 0. So 0 here, okay? The next is 2 0 minus 2 and 0. So 2 0 minus 2 and 0. The next is 1 0 minus 1. This is your 1 0 minus 1 and then 0. And now the last row, that is all 0. Now if you just multiply the corresponding this locations there, 4, 3, non-zero, right? So what will happen if you multiply them? Because again, we don't want these pixels to participate here, right? And these pixels will not participate. Why these pixels will not participate? Because corresponding to this one, you can see here, corresponding to this one here, we are having this 0 here. So it is not participating. Similarly, corresponding to this 2 here, we are having 0. So it is not participating. So that is how we got this response as -4. So you must be wondering what am I doing? Just see, a simple trick may help us. So this is how we have constructed the first column of the transposed convolution, that is right, matrix. Now similarly, when we are going to, so once this is done, then now we are supposed to slide our filter. So now our filter will be placed here, and this time what is happening, these 9 pixels will participate, these pixels will not participate, and we will get this output here, right? So can we generate the second, the output, the second layer of this second column of our transpose convolution? So in the second column, what is happening? How we need to append 0? The 0 should be here, right? So like this. So how you have written here? See, this 0, 1, 0, minus 1, 0, 1, 0, minus 1, then 0, 2, 0, minus 2. See here, this 0, 2, 0, minus 2, and so on, right? And when you are going to do the convolution here now, it is going to give you this 4, right? You can check it also. You just check it, right? Okay, so now, so we have constructed 2 columns. Similarly, now what will happen? What my filter will, because now my filter will cannot move right. Now my filter will go here 1 step down. And then what will happen? These pixels will not participate. So we will generate a mask correspondingly, right? So just generate the 2 masks, because see, why these all 4s are 0? Because we know that when we have moved this filter here, okay, when we have moved this filter here, these pixels are not participating. So first 4 zeros will be there, right? And that is how you can see the first 4 zeros are here, right? So similarly, we have constructed this third and the fourth column. And once this transposed convolution matrix is created, we can multiply it with the output of the convolution. See, this is your output of the convolution. Convert it into, because we wanted to convert this, we got it from 4 cross 4 input. Now we want to convert this 2 cross 2 input into 4 cross 4 input, right? So just convert into 1D vector, right? So we are having this, and just perform this convolution here, right? So what this first will give me, this multiplication here. Now do the simple multiplication here. So first will give me -4, right? Second will give me 4, third will give me -8, like that, right? So the output will be the 16D vector, and we can rearrange it in 4 cross 4 array, right? So that is the output of a transposed convolution. So is it clear to everyone? Any question on the transposed convolution? Okay. So this is how upsampling. Now, as I told you that there are some other upsampling operations are also there. So one is your nearest neighbor, in which the new pixel is assigned the value to its nearest neighbor here, right? So here you can see that in between this every pixel here, right? So 4, next is 4, now next to 3 is 3, like that. So this is how from 2 cross 2 you generated 4 cross 4. Now there is another very popular method, that is your bilinear interpolation. Now in the bilinear interpolation, what is happening now, in between 40 to and 30, you need to insert 2 values, right? So what if for this value, what will be there? Influence of this pixel will be more. For this value, influence of this pixel will be more. So what we'll do, let us say we need to calculate this. So this 40 will be given, because now 4 values here. So we are dividing it into 3 parts, right? So 40 multiplied by 2 by 3. So 2 by 3 weightage is given to 40, because this position is closer to 40. Now what is happening? We are going to give 30. What is the weightage? 30 multiplied by 1 by 3. So if you do this, you will get this 37, 36 point something, right? That is 37. Similarly, if you have to calculate for this, so what will happen here? This time 40 will be given weightage, this 1 by 3, and this 30 will be given weightage as 2 by 3. So 2 by here for this position, 2 by 30 into 2 by 3 into 30, and 1 by 3 into 40, and that is how you will get. So this is the bilinear interpolation, but here for we use transposed convolution. Now there are a couple of studies I will go through quickly, so just to give you an idea that what are the work our students are doing. So we are also working on segmentation. So this one, although this image is for polyp image, but this work is done by some other students. Purnima, you are already aware, yeah, Purnima Singh Thakur, and another student there, Nishant Khare. So here, this simple encoder decoder model was created, and we have checked we have actually created this model to analyze the loss functions for image reconstruction. So if time will be there, I will just tell you the autoencoder which are being used for this is an for the image reconstruction, not for segmentation. But I mean, it is used here as segmentation. So when we are passing it this input image, so this is the latent space which is learned by this encoder, and then this is the segment image which is being produced, right? So here this is these are all your original images, these are your ground truth, and this is your predicted truth, right? So between these two we can calculate the result, like dice coefficient and all those which I told you. Now, this is another work. This is the work by Samir only. It is presented in a conference. So, wireless capsule endoscopy, that is basically a very promising technology to investigate the gastrointestinal tract. And here he made use of these two data sets for polyp segmentation. So basically, here now he used these, because see what is happening, this you just focus on unit, right? Because there are so many other nets, so it is not possible to cover all. So segnet, PSPnet, FCN, so here use for these encoder decoder model, right? Which convolution, see, skip, try to understand why these skip connections are being introduced. Remember, I told you yesterday also that when we go for gradient descent problem, then what happens that we are having problem of vanishing gradient, right? So what, yeah, I will, don't worry, I will share the slides also. We'll put it on that folder only. So what is happening? As I told you there, that what happens? So let us say sigmoid, right? They are the very popular functions for activation functions. So what happens when you calculate gradients? Every time its value is smaller, and then you are going to multiply it, right? So if you are going to multiply 0.5 with 0.5, what is happening? 0.25, right? So further smaller. So what happens that ultimately the gradient magnitude decays, right? Your gradient decays and your network doesn't learn anything and it dies, right? So that is why we need solutions. And one solution was, as I told you, to replace the activation function. That is how, along with the, for gastric cancer, Samir will talk later. So here, one thing is that we have changed the activation function, and other methods are also there, better training, right? So in that, then the ResNet came, which gives you skip connection. So skip connection are to help the decoder so that your process may be better learned, right? So in this, okay, let us come back to this work very quickly. I need to finish. Samir has used these three networks, right? With you, just consider here with unit, because unit, now you are aware, right? So in unit there was a CNN. So in the CNN he used ResNet, VGG, and MobileNet, right? And then he chosen, okay, this two category binary segmentation, and for loss, so he has chosen this binary cross entropy loss. So other details are for the training of model, right? All those things. So these are the result observed. So you can see that this on this data set, the results are shown on the two data sets, right? And you can see here the what is the this IOU and MIOU, mean intersection over union, right? So that is given, and it is, you can see that the performance, right? So you are getting with unit, right? With unit you are, and this you are getting better performance with mobile, right? So these are the qualitative results. Here you can see that the ground truth, then the mobile net unit with mobile net and segnet with mobile net, they were giving you these results. So this is what do we mean by segmentation results. So I will skip this. This is another study which is done by Shubhangi. I think this paper we have already submitted. So this is the smoke detection model. So here again, you can see this smoke is supposed to be detected here. So I'm not going to the detail here, just see this is smoke, and here this is the segmentation. Now here, see, so the here you can see the three classes there: person, here smoke, and then so these are the results, original image, then here these are the ground truths, and these are the predicted image, right? So this is what we mean by segmentation. Now I think this is another study we have just submitted in a conference, but I would like to tell you, so I mean, instead of going to this, we again here in this study also we have used a shallow unit. Okay, I'm skipping this. So quickly before, because I would like to go back so that I may tell you about this CNN, how we are using them for image reconstruction. So I didn't want to come back after so many slides. So let me tell you about my group. So usually yesterday, actually, many things are being combined, and I mean, the time was not much. So I could not tell you that we have this IB group, Image and Vision Engineering group at our institute, where we are mentoring, we are having many students working with us. So the PhD students are shown here, and I'm sorry I could not include two more young people, Abhinav and Rohan, who are our MTech students in the lab. So here's with, you have already met with Samir, Purnima, Shubhangi. These are the other three members, right? Nishant is there, then Amit. Sudha is the youngest. So she has just, I mean, last year only joined our lab. So now let me tell you very quickly one more thing before ending my this thing. Just very quickly, I will tell you about this autoencoder. So till now we said this unit encoder decoder models, which were basically supervised. So for segmentation, you need to provide the ground truth also. Now we can use here, I'm telling you about autoencoders. So autoencoders are also neural network, which are trained to produce the this input, right? So again, what happens that your encoder learns, right, the compact representation of the input object, and then your decoder decodes it, and it can construct the original picture. Of course, some loss will be there, but this code, or you can say latent space, that is the much smaller size, and most important features are being captured, right? So I will not go here. So remember that what autoencoder does, autoencoder actually learn the representation, or you can say encoding, so that dimensionality reduction can be done. And they ignore, once neural networks, they are being trained to learn the data representation, then they ignore the noise present in the data, right? So along with the dimensionality reduction, your data, your neural network also learns how to encode this, right? So that is why we are calling it as autoencoder. So remember that autoencoders are data specific. So if you have trained your autoencoder for a particular data, it's the same will not work on other data, right? It is a lossy, definitely your latent space, right? Your encoder learns the important thing, but still this is not the exactly same, right? It is quite same, but not the exactly same, close. So it is a lossy one, right? And it is an unsupervised. So you need to provide here the examples, right? And your autoencoder learns from those examples automatically. So this is the example of use of this encoder decoder architecture for image reconstruction. So you can store this latent space, and later on, when you want, you can reconstruct your picture from this later. You can see that not exactly same, right? Some loss is there. Similarly, this is another example, original image, and this is reconstructed image. But okay, it depends upon whether you can work. So I will skip this example. Now, this is your convolutional autoencoder, right? You can see this encoder block and this decoder block. So encoder block will perform the convolution, decoder block will perform the deconvolution. The same thing is there. The auto encoder decoder model, which I told you for segmentation, that was supervised. So you are supposed to provide here ground truth also, but here you are providing it examples and it is learning. So this is your convolutional autoencoder where you can see this, okay, again, this picture is there. Now the convolution layer, pooling layer, this is your encoder. Encoder learns this latent code and then deconvolution. Remember always for deconvolution, we will use transpose convolution. And then the image is reconstructed, which is quite close to the original. Right? So, okay, I think I must stop here. This I will upload, you can go through this example. Yeah. Okay. Yeah. So thank you so very much.